Hello, my name is Lori Prokop, and I have the pleasure of introducing to you today uh, the results of a collaborative effort between myself and several other authors who I'll introduce on the next slide. The results of work that is a compilation of case studies of successful autonomy applications in operational spacecraft and how they were tested and verified. But before I go into the next slide, I just wanted to say a few words on our motivation for this. So autonomy is progressing all around us. There's increasing autonomy in systems, and that's no different than space systems. The autonomy in space systems is also increasing. And we thought that along with that increase, there is also an increase in concern in how do you test these autonomous systems? How do you verify them, and how do you trust them? But what we realized was that there are good examples of autonomous systems that NASA uses routinely and has used, and they have been successfully verified. And in cases such as, especially when there's a short time to effect, or when there's communication loss or communication delays, that has driven the need for autonomy in space systems. So we bring to you a set of case studies, and I'd like to introduce the authors of those. This is in order, chronological order of the way they appear in the paper. We thought we wanted to cover a broad range of space and spacecraft and launch vehicles, as well as consider all mission phases and criticality. So our paper is organized in chronological order from ascent through utilization: ascent phase, transit phase, descent and landing, and then science utilization phase. Our contributor for the ascent phase is Dr. Stephen Johnson out of Marshall. Dr. Johnson is currently the Mission and Fault Management and Analysis Lead for the SLS program. His section is the Space Launch System SLS Fault Management System. And next, also in ascent phase, my tech fellow, Dr. Dan Dorney of the NASA Engineering and Safety Center, the NESC of Langley, provided the section on SpaceX Autonomous Flight Termination System, AFTS. In transit phase, I provided the section for that, Dr. Lori Prokop, and I'm also a NESC Tech Fellow for software, and I did my section on the Orion OpNAV, optical navigation application. Dr. Feather is out of JPL, and he provided two sections, two case studies to cover descent and landing with the DIME system, and in science and utilization phase with the Aegis system. Dr. Feather is currently a principal engineer for software assurance at JPL. So the way I'm going to go through this is just one case study at a time, and we'll the first case study we'd like to share is ascent phase, a human-rated autonomy system that serves as the fault management system for NASA's SLS rocket. So for SLS, it is the next generation human-rated deep space launch vehicle. You can see a graphic on the right. It's intended to boost humans and cargo beyond low Earth orbit. The autonomy in this system is needed not only for the nominal flight, but also due to the time to criticality, the off-nominal, because of rapid failure propagation and all the high dynamics during ascent. The key driving requirements stem from NASA's NPR 8705 human rating requirements, and are summarized here. Autonomous operation is required for functions that, if lost, would result in a catastrophic event. It should isolate and recover from faults. There's the failure tolerance requirement, And there is an abort capability requirement from launch to Earth to protect for complete loss of thruster control. The fault management system itself is a monitor response system, and it's specified by DVOs, detailed verification objectives. The nominal part of the autonomy is verified in the SIL. But the fault management off-nominal cases are much more difficult and challenging because of the numbers. So in order to verify these, yes, each algorithm is tested, but there's also an extensive analysis effort undertaken to both quantitatively and qualitatively assess the benefit versus risk of each algorithm against all of the scenarios. So they're estimated, they're evaluated quantitatively for their benefit to loss of crew against each of the scenarios, and then a team of experts qualitatively goes through and makes judgments on the need versus value. The second case study, also during ascent phase, is with the launch termination system of the SpaceX Falcon 9. So it's called the Automated Flight Termination System, AFTS. The launching of vehicles is very complex and energetic, as previously discussed, and there are many safety precautions and protocols. The time to criticality is can be below human reaction, so there is a need for increased autonomy. Historically, though, there is a range safety crew on the ground that does active monitoring, but this has been becoming more automated, and this is one example of that. Falcon 9 used to use a traditional flight termination system, but now has transitioned to this automated as of 2017. So the AFTS has a core software package that was jointly developed by NASA, the Air Force, DARPA, and then that core package can be used on multiple rockets by putting a customized wrapper around it. Some of the design features include, it is independent from the launch vehicle, a high reliability, single fault tolerance, and capability to have telemetry throughout all the mission phases. It's also very versatile in that you can plug in multiple sensor types for position, velocity, attitude, different inertial navigation systems, things like that. And another feature is that it's highly configurable with rule-based algorithms depending on what is needed for that particular flight. It's data-driven, so these mission rules, they're developed basically from the inventory of rules from what the humans had during flight safety practices. So this is a picture of some of the hardware. It uses a redundant chassis with a lot of redundancy built in on the sensors. And then it has that launch vehicle specific wrapper. It was built and designed to NASA design and construction standards. All of the failure modes are reflected in a hazard studied and put in the hazard report. And it was gone through, this was one of the key parts of the test campaign, is tested on sounding rockets and operated in shadow mode. At least for the Falcon 9, it was in 13 flights on shadow mode before it became operational. So it has been used on the Falcon 9 ever since 2017, and this system is believed to provide a 50% reduction in range-related expenses. We move on to transit phase with the Orion Optical Navigation System. This is a system that processes optical images for autonomous navigation of the Orion capsule. If there is a communications loss, it's a safety critical code. It is essentially a commercial camera mounted, fixed mounted underneath the capsule in between two star trackers. And on the Artemis 1 mission, this is sort of a graphic of the what we call passes, the times that the sensor is activated. The Earth being in the middle and the moon being blue, outbound mission, it takes readings of either the Earth or moon to determine where it is. And then for Artemis 1, presumably would be on to take control of the vehicle in the event of communications loss. Basics of the software is images are processed in real time during these dedicated OpNAV pass times. Takes a still image of the moon or the Earth and calculates range and bearing from that. For Artemis 1, it's range and bearing. For Artemis 2, it's being extended to add self-attitude determination. It calibrates itself and undistorts images in real time and is safety critical, developed according to NASA's standards, NPR 7150 and CMMI. So the test campaign of OpNAV really relied on testing against some key performance requirements on accuracies. And it had a whole list of, I guess, types of reviews, the life cycle reviews, full coverage unit testing, code inspections, verification, off-nominal, and robustness testing, and will be validated finally on the outbound leg of Artemis 1. These charts here just show some quantities. There's extensive synthetic images used for testing and many off-nominal cases used to gain confidence in the system. And this is just a graphic that just has some sample test images, nominal ones being from a large Earth to a small dimly lit moon, and other off-nominal images with debris or sun flare, things like that. On to entry, descent, and landing phase with the Mars Exploration Rover, DIME system. So in 2004, there was successful entry, descent, and landings of 2 Mars exploration rovers. This graphic shows sort of the phases of landing, where the parachute slows descent, then rockets cancel velocity and airbags cushion the final drop. The DIME system plays a role in this canceling velocity aspect of the descent. So DIME stands for Descent Image Motion Estimation System. And this was added to the MER rovers in descent because of the danger that some unpredictable crosswinds might add additional velocity to the landing that may exceed the capacity of the airbags. This was discovered late in the design, and this automated system was added to potentially tell the rockets to fire if there's too high of velocities, and it was used on one of the landings. So what it does is during descent, it takes photos of the ground and picks a feature on the first photo, and say takes a second photo and identifies that same feature, and then deduces the horizontal velocity by comparing successive photos. The requirements on DIMEs, one of the main interesting ones is the do no harm probabilities that were put on this project. Similar to OpNAV, where it did not want to report a value out of spec, it was much more preferred to not report an output, because you didn't want to fire the thrusters and possibly interfere with the landing. Versus providing an incorrect value. So the do no harm requirement percentages are there, and it was an autonomous system that was designed to predict hazards and avoid them by design if possible. And it was also interesting that this system provided like 4 sets of outputs and determined their plausibility if one output was good, it would serve it. It would provide that as output. And simulations and field tests were used to be as representative as possible for testing. Finally, in the science, the ultimate goal, I would think of space missions, is to ultimately gather data for scientific discovery and exploration. So this is an application of autonomy to maximize that science benefit. There's several papers on this. This is the Aegis system. So at the end of what it does is, at the end of a sol, it autonomously picks targets and does science, and different science depending on the vehicle, so that in the morning the vehicle can be off and running. So for Opportunity's case, it takes a panoramic picture, it identifies the most scientifically interesting object, it points a narrow field camera to it, and then takes a photograph. On Curiosity, it does the first two steps the same, but then it uses a laser and points a laser at it and zaps it with the laser to get some measurements. This is a picture of the Aegis system, autonomous exploration for gathering and increased science. It shows that it looks at several targets and identifies which of these is ranked the highest. The one in green would be, say, the winner. Then it plans and executes the trajectory to point the laser or the camera to perform the science, and then takes the science measurement, whether it be a photo or a zap. It also has watches out for some danger conditions. It doesn't want to hurt the instruments or interfere with higher priority things on the vehicle. So don't point the camera at the sun, don't zap the rover with the laser, and stop gracefully if anything weird happens. So in this case, this autonomous system should enhance, but is not essential. So it's crucial that it be low risk. It was based on a heritage evolution of algorithms for identifying rocks. It ranks the rocks defined by scientists and performs its own safety checks. The testing of this system was done using a variety of images from Martian terrains in simulators as well, and in rovers on large terrain sandbox. And many nominal and off nominal images similar to the OpNAV test campaign. There was a progressive checkout, and then the success on Opportunity paved the way for Curiosity. The benefit is that science is being obtained that would not have normally been obtained, and it actually performed better than the random targeting. So conclusions to these 5 case studies is that autonomous systems have been employed and verified in both launch vehicles and spacecraft. And in fact, the automation is necessary, especially when there's time criticality and communications delay or loss. And I think these provide good examples of successful verifications along a broad range of domains. There's across all these mission phases that we spoke of on launch vehicles and spacecraft, and in different criticalities. So, what's the common theme through all of these? I think through looking at them, obviously, there are lots of testing. There's all kinds of testing. There's analysis type tests. There's tests and environments with different fidelities. And in all of these, I believe there's a concerted team, time and effort that was devoted not only just to the nominal cases, but also an extensive off-nominal set to minimize false positives. And that concludes the presentation. I thank you all for your attention. I hope this gives you a taste for the paper, and please feel free to reach out to any of us authors for further collaboration. Thank you.